Hello, everyone. My name's Arushi, and I'm a grade 8 student from Toronto. Today, I'll be talking about how I used Python for planet defense. In particular, how I was able to measure the success of NASA's DART mission. Asteroid collision risks are real, and sometimes they do happen. Just 1 year ago, a 1-meter asteroid whizzed past the CN Tower right next to my hometown, but luckily, it fell near in Lake Ontario harmlessly. But this showed that asteroid collision risks are real, and actually smaller the asteroid, the higher the impact probability. Currently, hundreds of near-Earth asteroids are being discovered every month, and this is outpacing their analysis by the astronomy community. And analysis is very important, because if an asteroid were on collision course with the Earth, we would need to know their physical properties, like size and strength, to be able to deflect it. I'm sure you guys have all heard about NASA's DART mission, the mission where last year they tried to impact a binary asteroid system that changed the mutual orbital period. Mighty NASA projects inspire imagination, and this made me think, what if I, myself, could create an algorithm to measure the physical properties of near-Earth asteroids? What if I could apply it to the Didymos binary system to be able to measure the physical properties before and after the impact? And finally, what if I myself could actually determine the success of NASA's DART mission? My whole project was based on open science, whether it was open telescopes, which accepted the research proposals from citizen scientists, which allowed me to observe the asteroid, or open datasets, which assisted me in finding known objects in my image, or even simply open communities where I could reach out to whenever I needed help or was stuck on a very hard issue. Of course, one thing I cannot forget is open programming languages and libraries, which often helped me during my project. So this is a map of all the telescopes I used during my research. These telescopes were spread out all around the world in places like Canada, Chile, and the United States. In whole, I got over 55 hours of observations of the Didymos binary system. These observations were spread before, during, and after the DART impact. How did I analyze these images? First, I found all known objects in my image. This included known stars and known asteroids. I then created my own algorithm to centroid them. The second part was actually measuring the brightness of the asteroid. To do this, I created apertures of different sizes, an inner aperture to measure the brightness of the asteroid, and an outer analyst to measure background noise. Finding the aperture size was very hard, and I used slope analysis to help me. Third, finding comparison stars. My observations were sometimes very long, which meant observing conditions like weather and air mass did change. To account for these, I used comparison stars, stars with a known and fixed brightness. By measuring their change in brightness caused by weather conditions, I was able to apply this to the asteroid to eliminate all these changes. But this wasn't enough, which took me to my fourth step. Asteroids are always in movement, and as they move, their distance from the Earth and the Sun always changes, causing changes in the brightness. To account for these, I applied offsets to benchmark the brightness of the asteroid to one astronomical unit from the Earth, one from the Sun, and at a zero phase angle. Now was the interesting part. I had my light curves, and I had to find the rotation period of the asteroid. As asteroids rotate, different sides reflect light differently because they are irregular in shape, and this causes two maximas and two minimas in their light curves. And in the case of the Didymos binary asteroid, there was a moonlet. So, by subtracting the rotation period from the original light curve, I was able to find the mutual orbital period events. So I applied my algorithm to the Didymos binary system and got 7 interesting results. First, I found the absolute magnitude of Didymos to be 18.03 and its size 820 meters. Second, I used root mean square error and concurrent modulo to find the rotation period and found it to be 2.26 hours and did not change after the impact. Third, I measured the mutual orbital period of Didymos and Dimorphos and found that it actually reduced by 35 minutes post-impact. Fourth, I measured an increase in the brightness of Didymos of 1.2 This was caused by all the debris around the asteroid right after the impact, reflecting sunlight. This ejecta, I also measured the length, and it came to 20,000 kilometers, which is quite a lot. Sixth, using the rotation period and the size of Didymos relationship, I was able to determine that it was very likely rubble-based. Seeing all the masses of ejecta ejected from Dimorphos, I saw that Dimorphos was also likely rubble-based. So now is the big question. Did we actually move Dimorphos? And the answer is yes. After measuring the 35-minute decrease in the mutual orbital period of Dimorphos, and by applying Kepler's third law, I was able to find that a 40-meter reduction in the orbital radius of Dimorphos happened, proving that deflection was in fact successful. All my results were very closely validated with NASA, proving that my algorithm was successful. I believe that no project is actually completed till outreach is done, which is why I've made several presentations at places like the Royal Astronomical Society of Canada and during Asteroid Day to bring awareness about astronomy and planetary defense. I've also created online training modules to basically ignite the fire in the minds of the next generation. In addition, I've made several publications, one of which is in the Royal Astronomical Society of Canada's journal. So in conclusion, my algorithm was successful in determining the physical properties of near-Earth asteroids and measuring the success of NASA's DART mission. It shows that open science can be used by citizen scientists to actually support space missions. I have several plans in the future, some of which is to contribute to other space missions like the Hayabusa 2 from the Japanese Space Agency and the OSIRIS-APEX. I would also like to expand the photometric techniques that I used in this project towards exoplanets and specifically their atmospheres. So thank you so much. And if you or your organization has any time on robotic telescopes, it would be really great if we could collaborate. Thank you.
Well, that is very impressive. So we have time for some questions. Are there any questions online?
Not so far.
Okay, just want to make sure our online audience feels included. Are there any questions in the room?
Hi, very cool research. Didymos impact was awesome. DART was really cool. And it's really neat that you managed to get good agreement with the values measured by NASA. That's really, really cool, especially using this open resources. Part of what I was wondering is what further resources would you have wanted to have access to that could have made this process easier for you or for other citizen scientists who want to participate in this way?
That's a great question. Thanks. And I think one of the main goals of my project was so that it could be done by data that's publicly available, open resources, so that anyone can replicate it. One thing I did find is that I think that several open data sets were slightly harder to find, one of which was perhaps the active database. So I think raising awareness and actually publicly advertising all of these open data sets that are available to everyone is a big factor that needs to be done.
Are there any other questions?
Yeah, amazing talk and amazing work. Very impressive. Were you able to make any measurements of the ejecta cone, angle, impact, things like that?
So far, I'm still currently working on making more measurements of the ejecta. I started by measuring the ejecta length, which I found the max to be 20,000 kilometers. But now I'm looking on actually creating apertures of different sizes to measure actually where the density of the ejecta came from, and perhaps even do further research on the angular momentum.
Have you looked at any of the data coming from the Italian Lizia cube and specifically looking at the ejecta cloud?
Not yet for sure. But I think looking at data from both the Draco camera as well as the data that was captured by Lycia Cube would be very interesting because this would allow me to get actual close-ups on the asteroid, whereas all my previous research has been done from ground-based telescopes.
Let's talk. I'll put you in touch with the PI for Lizia.
That would be amazing. Thank you.